Hello everyone, my name is Kevin Aldairi Barribarra, and today I will talk you about mobile offshore drilling units, a key technology in offshore oil and gas exploration and production. First, an introduction to offshore mobile drilling units. These units are designed to drill in deep water environments using advanced technology that ensures efficient, safe operations with minimal environment impact, and they represent the most advanced and challenging edge of marine engineering. The mobile offshore drilling units are platforms designed to drill in deep waters. These units use various technologies to operate efficiently and minimizing environmental impact and optimizing production. Okay, now the importance in the offshore industry. In today's energy landscape, mobile drilling units are indispensable. They allow us to access oil and gas reserves that will otherwise be unreachable. Their versatility and ability to adapt to extreme conditions ensure a steady energy supply even in remote and harsh offshore environments. The mobile drilling units are crucial for accessing oil and gas reserves offshore. Their, flex, their, flexibility, their flexibility Their flexibility and advanced technological capabilities allow them to operate in adverse and unconventional conditions, ensuring energy supply. Um, okay, now the presentation objectives. The goal of this presentation is to give you a comprehensive understanding of mobile offshore drilling units and their technology. We'll cover technical and operational aspects, as well as their importance in the industry to support informed decision making. Now, the drilling technology. We have the marine drilling units. The marine drilling units can be fixed or mobile, submersibles, jackups, semi-submersibles, drill ships, and TLP spar platforms. Jackups operate up to 19 meters, withstand waves of 6 to 9 meters, and winds over 120 kilometers per hour. And semi-submersibles operate in waters up to 500 meters, are stabilized by pontoons and anchors, and resist severe sea conditions. Now, the dynamically positioned platforms. Dynamically positioned platforms maintain position over the well without anchors. A major innovation are these platforms. These platforms do not require anchors. Instead, they use thrusters and computer-controlled sensors to stay positioned over the well, even under changing wind and current conditions. They are essential for drilling in waters deeper than 2,000 meters. We have the anchored semi-submersible platforms. These platforms are floating structures anchored to seabed. Their design allows superior stability in adverse conditions, making them ideal for offshore drilling. The anchoring the ensuring system is crucial for safe operations. They have 3 to 4 legs per side, joined by pontoons that store water for partial submergers. These are designed for open sea, operate in deep waters with strong winds and heavy waves. The modern versions have triangle hulls, multi-hulls designs, or French pentagon designs, offering high stability and symmetry. Now we are going to see the oceanographic parameters and related systems. First, we have the relevant oceanographic parameters. These are proper planning of offshore operations relies on oceanographic parameters like water temperature, salinity, currents, tides, wind, and wave weight. For example, tropical storms in the Gulf of Mexico have produced waves up to 10 meters. Such conditions demand precise mooring and platforms designed to ensure operational safety. Oceanographic parameters are like water temperature, salinity, or other essential for planning drilling operations. These factors affect platform stability and drilling technique effectiveness. The design and operation of marine platforms depends directly on waves, ocean currents, tides, and winds. The mooring system must be calculated based on these parameters. Next, we have the subsea wellhead systems. These act as the interface between the drilling platform and the well. These systems allow fluid circulation control, and their design must be adapted to specific seabed conditions. They include a permanent guide base, high pressure seals, tubing hangers, and valves. Models like Cooper Cameron STC-10 and STM-15 or FMC UYD-15 capable or handling up to 5,000 psi. Now the components. The permanent guide base. These guides tools during drilling, and the seals can be elastomeric, metal to metal, or combined. The Cooper Cameron, like the STC-10 and the STM-15, with working pressure of 10,000 to 15,000 psi. The valves and connectors control the pressure and connect to the subsea tree, and the tubing hangers suspend pipes at the various depths. The FMC UYD-15 have a capacity for multiple hangers and high pressure resistance. Okay. The subsea well planning. The subsea well planning requires a detailed multidisciplinary approach. It involves data collection and analysis, overburden pressure calculations, fracture gradient evaluation, pipe settlement, and foundation design. It also includes wellhead structural analysis and the estimation of abnormal pressure or shallow flows, which can greatly impact well integrity. The planning subsea wells requires a meticulous approach considering the geological and oceanographic factors, road Road selection and well design depend on detailed evaluation of subsea conditions. Now we are going to see the system operation and analysis. We have the unconventional tools and cementing. The unconventional downhole tools play a critical role in a modern subsea drilling and cementing. We have the laser cutting for precision on pipes or structural components, abrasive water jet for cutting stainless steel or high pressure equipment, ultrasound for valve and injector cleaning. Cementing is used to secure drill bits, stabilizers, collars, and bottom hole motors, as well as for extending the life of tools like wireline or slickline under constant wear. We have some examples like downhole tools, laser cutting for precise cutting of pipes, plates, or casings, abrasive water jet for cuts, stainless steel pipes, pressure equipment, or removes coating without damaging the base material. We have the ultrasound that cleans valve components, injectors, or measurement devices. Next, we have the cementing of drill string parts, such as bits, stabilizers, drill collars, and bottom hole motors. Next, we have the valve and connector components that increase wear resistance from high speed fluid flow. And for final, we have the well intervention tools like slickline, wireline, cemented to extend turbine life under constant friction. We have the subsea control systems. The controlling subsea operation at great depths requires highly specialized systems like hydraulic valve systems that sample and reliable but limited in deep water, electrohydraulic multiplex that combines electrical signals with hydraulic actuation, fast and effective for deep water and complex tasks. We have all electric systems, use only electric actuators, clean, low maintenance, but still evolving. And we have optical electric system, use fiber optics for high speed data, and this is very efficient for fragile and expensive. We have the wireless system, ideal for backup or remote inversion, but limited by slow speed and interference. The subsea control system are essential for monitoring and managing operation on the seafloor, ensuring rapid response to changing conditions. We have some examples of the subsea control systems like valve-based systems. The advantages of this one are like simple design. These one are reliable at shallow depths. It have some disadvantages like slow response, inefficient in deep waters. Next, we have the electrohydraulic multiplexed systems. This one uses electricity to send signals and hydraulic fluid to operate the equipment. The advantage are the fast control, suitable for multiple functions and deep waters, and the disadvantage are like more expensive and complex. Now we have all electric systems. These are fully electric, controlled with actuator and signal, not fluid, and these have no fluid use. The advantage of this one are clean, less maintenance, more efficient, and the disadvantage are technology is still evolving for large scale use. Now we have the optical electric systems like fiber optics. It works with fiber optics, combines electric power with fiber optic communication. The advantage are that they have high data speed and ideal for smart systems. And the disadvantage are that they are expensive and delicate to install. Now we have the drilling resource. The drilling resource are vertical conduits connecting the platform to the subsea well, allowing safe fluid and tool transport. The main types are marine riser, BOP on seabed, used in deep waters with floating platforms. Next, we have the surface BOP riser. BOP on surface, used in shallow waters with jack-up rings. Next, we have the tieback riser. It connects subsea wellhead to surface BOP, useful in production or pre-existing wells. And next we have the workover riser, lightweight and flexible, used for maintenance or repair of subsea wells. Riser and are pipes that connect the platform to the subsea well, enabling fluid and tool transport. Their design is critical to maintain structural and operational integrity during drilling. Now, the drilling, completion, and workover risers. Riser analysis include the static and dynamic and fatigue. The are the stress from self-weight and internal pressure. The dynamic are the response to waves, currents, platform movement, and the fatigue are the service life based on load cycles. The common components are the telescopic joint, flexible joint, gimbal, tensioning rings, keel and choke lines, wellhead and BOP equipment. The riser common components the riser design and analysis. The subsea tree structure is a structure that controls flow from a production or injection well. It have two types: horizontal that offers better access, no guidelines, ideal for deep waters up to 5,050 meters, and vertical. It has simpler control used in completion with guidelines. The components are the connector, the gate bulbs, actuators, choke, tree cap, protective frame, and the installation with specific tools like wellhead installer, tubing hanger installer, bushings, testing, and orientation tools. In conclusion, in summary, mobile offshore drilling units represent an advanced combination of engineering, technology, and strategic planning that enables the exploration and extraction of resources in extreme environments. Their proper design, operation, and maintenance are essential to ensure the safety, efficiency, and sustainability of offshore projects. As we've seen, mobile offshore drilling units are incredible complex systems that combines advanced engineering, geoscience, and real-time control technologies. Their proper design, planning, and operation are critical to the success of offshore engineering projects. Thank you for your attention.